Hello everyone, I'm Sizhe from Carnegie Mellon University. Today on behalf of our team of 4, I'm here to present on transformer-based indirect structural health monitoring with attention-driven detection and localization of transient defects. So to start with, currently the broken rail detection world is transforming from a reactive to a real-time manner. So this manifests into our research objective of our project, which is to create an onboard monitoring and computational embedded technology that automatically detects broken rails as they occur in collaboration with lab tech cooperation. And this is quite a long research objective, so let's break it down a little bit. So onboard monitoring refers to these sensors embedded on the locomotive, which could be these vibration sensors that are accelerometers collecting acceleration, or it could be these vision sensors that are cameras capturing images. And computational embedded technology refers to the capability to detect anomalies online. And broken rails as they occur refers to the fact that we want the detection to be done prior to the next train passing. And despite these technological advances, broken rail detection remains largely grounded in manual inspection and these fixed systems like wayside defect detectors. And on the other hand, the current transition to indirect monitoring at research level has already shown many benefits, like a longer coverage, finer resolution, or like a lower deployment and maintenance cost. However, indirect monitoring does have its own problem that's currently hindering the transition from research level promise to industry level practice. And some of these drawbacks include, for example, limited sensitivity to small defects or like noise contamination, and all of them adding up further restrict the generalizability of different systems or algorithms across different trains, speeds, and conditions. And in the meantime, some researchers decided to push the boundary of indirect monitoring even further by incorporating AI and multi-model systems. And these systems aim to detect broken rail by fusing both the vision and the acceleration data. However, we also like to point out that due to the lack of efficient way to validate and standardize these approaches, the development of these approaches is still very much at a research level. So in this presentation, we'll focus on one side of the multi-model system, which is the acceleration side. We'll work around the sparse data limitation and use synthetic data that we generated after comprehensively studying the literature and the real-world data that we collected to understand why are these, false positive or false negative being predicted by different anomaly detection models. So that's why we developed this 8-stage synthetic benchmark with incrementally complex realistic onboard indirect monitoring challenges. And incrementally here means that each new step or each new stage within the benchmark is built upon its previous stage. And within the benchmark, we further add in 2 key types of anomalies that is very commonly seen in indirect monitoring in literature, which are instantaneous spikes and subtle local deviations. And actually, the initial benchmark stage is not that complex, right? It's just a sinusoidal wave with different white noise. It only serves as these fundamental step of the whole benchmarking process. And basically almost all anomaly detection algorithm can point out whether an instance is anomalous or not. And if you further look at the spiky instances, you can see the spike itself is actually very much observable. The detection can even often be done with only manual efforts. And the same with local deviation. And on the other side, this is where after we adding in multiple layers of interference, we now are having these highly complex signals. And this is also where many existing models is already starting to fall apart due to these different layers of complexities. And then this benchmarking basically aimed to answer the question of what systematically introduced these complexities that lie between these two extremes? And how do these different layers of complexity influence model performance in indirect monitoring? Is it because we have multiple channels now? Is it because the localized noise? And this is why we introduce these intermediate stages, because they're there to deconstruct signal complexities. For example, we have the second stage, which simulates these non-stationarity by incorporating speed variations. And they're basically implemented through these distinct mean sequence change in the signal's frequency and amplitude. And this step aims to test models' capability to distinguish normal operational variations and the actual anomalies. And for example, in stage 3, we further simulate these data from multiple sensors. So instead of having only one sensor, we expand it to a 2-channel setup. So in this case, each channel would have their own ranges for sample parameters like amplitude, frequency, or phase offsets. And these steps aim to test the model's ability to handle these multivariant inputs and localize anomalies affecting only one or a subset of the streams. Or, for example, we further simulate these varied anomaly prognoses at stage 6. We basically introduce these non-uniform likelihoods of anomaly occurrence across different sensor channels. These steps aim to reflect the fact that how some sensor locations in indirect monitoring are more likely to capture defect signatures. And in the second stage, for example, we further simulate these challenging interference by adding these transient high-frequency localized noise bursts. So this aims to mimic these real-world events like wheel flats or debris impacts. And these steps aim to test models' robustness against noise that can obscure these true defects. And in stage 8, we further simulate these operational impacts through the addition of these periodic truncated Gaussian impulses. And this step aims to represent these events like passing over these periodic structures like rail joints or rail slippers. And this step aims to test the model's ability to distinguish defects from these regular repeating patterns. So that's basically it about the introduction of our benchmarking step. And starting from the next page, we'll talk about some of the models that we use. So our proposed model is a attention-focused transformer that leverages both input and self-attention through reconstruction. And the input attention layer, first of all, weighs different input channels and end up shrink each time step into a one-dimensional embedding. And once all these time steps are finished shrinked into a one-dimensional embedding, these embedding will be inputted into the self-attention layer, and the self-attention layer is going to process these input across different time steps now to weigh how important are all these time steps towards the reconstruction of every single one time step. And once they're properly weighed, the multi-layer perceptron is going to expand the signal back to the original shape to finish the reconstruction step. And once the model like this is trained, we will detect anomalies either by high reconstruction loss, because if a instance have a high reconstruction loss, it means it deviates from the existing pattern of other common instances. And or we also detect anomalies through these attention maps. Basically, the attention map is the first layer of the self-attention layer, and by discussing or analyzing the deviations in these learned attention patterns, we're able to also detect anomalies. And within further benchmarking, instead of 2 of our models that are marked in red here, we further introduce 4 state-of-the-art anomaly detection models that are often used in indirect monitoring. To start with, some of them are the LSTM encoder-decoder shape or the CNN autoencoder. And these two are rather less complex, and they both they build on a LSTM or a CNN backbone respectively. And we also introduce a anomaly detection model called MSCRED. So its main basically innovation is instead of reconstructing the raw input, it reconstructs these correlation matrices across different channels that it built, and it basically detects anomalies from the reconstruction of those matrices. And the fourth model we introduced within our benchmarking is anomaly transformer, which is very similar to how we detect anomalies through attention map, where they would use these extra terms related to the attention map in the loss function. And each bar here is actually originated from a ROC curve that is generated with varying threshold for anomalies. And within the first four stages of benchmarking, we're able to show that the transformer-based models generally demonstrate a better AUC, while some of these other architectures are already showing these earlier sensitivity to these initial complexities. And for further 4 stages, we're also able to show that transformer-based models still do better, but we're also able to show that all 6 models all reveal this critical vulnerability towards the stage 7 complexity, which is these high-frequency localized noises. And from a computing time perspective, compares to our closest competitor, which is anomaly transformer, our attention-based approach is able to offer around 30% faster inference speed, which we consider it very crucial for future onboard deployment. And for final takeaways, first of all, we're able to show that high-frequency localized noise is a current bottleneck for indirect monitoring. And we're also able to show that compares to one of the most advanced anomaly detection model, which is transformer, we're able to offer similar performance with a faster inference time, which is very important for onboard deployment. And finally, our path forward will be around this continuously enhancing noise robustness, which we consider our attention-based model already fully prepare us for that process. And that's all about my presentation. Thank you.